Look around the room you're in and try to count the screws. You can't. Not because there aren't any, but because there are too many, and almost none of them are visible. They're in the chair, the hinges, the wall socket, the arm of your glasses, the case of the device you're watching this on. Strip away the paint and the plastic, and the world looks like it was stitched together out of tiny steel spirals. That's the version of the screw everyone knows, the fastener. But for roughly 2,000 years, nobody used a screw to hold anything together. The screw was a machine, and the thing it did better than anything else humans had ever built. Take a turn and convert it into a straight line. Slowly, precisely, and with an increase in force that gets close to absurd. Everything that follows comes out of that one property. It lifted rivers onto fields. It crushed olives across an empire. It raised buildings off their foundations. It aimed cannon. And then, at some point in a workshop in Roman Alexandria, it did something no other machine has ever managed. Somebody worked out how to use a screw to make another screw, and once a machine can reproduce itself, accuracy stops being a thing one craftsman has and starts being a thing you can inherit. That's the story. One idea, tracked across 17 centuries, ending somewhere you won't expect. If you're new here, this is Trade Archive. Before anything else, we need to deal with why this shape does what it does, because the whole story sits on top of it. Unroll a screw thread in your head. Take the helix off the cylinder and flatten it out, and what you're left with is a long, shallow ramp. That's all a thread is, an inclined plane, wrapped. And a ramp trades distance for force. Push something a long way up a gentle slope, and you can move a load you couldn't possibly lift straight up. A screw does that same trade, except it hides the distance by coiling it. Here's what that's worth. Take a screw jack with a 1-foot handle and a thread that advances 1/8 of an inch per turn. Walk that handle once around the circle, and your hand travels about 75 inches. The load rises 1/8 of 1 inch. 75 divided by 1/8 is 600, so in theory every pound you push with becomes 600 pounds of lift. 50 pounds of effort turns into 15 tons. In practice, you don't get all of it, because a screw is enormously wasteful. Friction between the thread and the nut eats most of the gain, often 2/3 of it or more. That sounds like a flaw, and it isn't, because that same friction is why the load stays exactly where you left it when you let go. A screw jack doesn't need a brake. It is its own brake. If you want to see what that means at scale, Chicago in the 1850s. The city was built at the level of a swamp and needed to be higher, so rather than tear it down, they lifted it. In January 1858, a 4-story brick building weighing 750 tons was raised 6 feet 2 inches at the corner of Randolph and Dearborn on 200 jackscrews. The contemporary account says it was done without the slightest injury to the building. It was the first of more than 50 that year. The technique was pure choreography. On one job, a half-block of Lake Street went up on 6,000 jacks, with 600 men each tending 10 of them. And on a signal, every man gave every jack a half-turn. 3/16ths of an inch. Then the signal again. The block rose 4 feet over about 5 days, and the shops stayed open the whole time. At the Tremont House, a 6-story hotel covering more than an acre, guests kept sleeping in their rooms. One noticed only that the front steps got a little steeper each morning. Nobody was straining. That's the point. A screw takes a force a person can comfortably produce and turns it into a force nothing else in the building can resist. And notice what the man tending those jacks gave up to get it. Half a turn moved that building 3/16ths of an inch. If you wanted it to move faster, you'd cut a coarser thread, more advance per turn, and instantly you'd have less force because the ramp got steeper. Pitch is the dial. Fine thread, enormous force, glacial speed. Coarse thread, quick travel, and now you need a crew again. That single trade-off is why there is no such thing as one correct screw, and why the shape of the thread itself became an engineering decision. Look at the thread on a bolt, and you'll see a sharp V, 60 degrees between the flanks. Those steep flanks act like a wedge, jamming the two parts together sideways as you tighten, which is exactly what you want when the job is to grip and never move again. Now look at the thread on a machine vise or a jack or a lathe lead screw, and it's different, squared off, or nearly so, a flat-topped trapezoid. That's an Acme thread, and it isn't trying to grip anything. It's trying to slide, over and over, for years, carrying load along its axis without wearing out or wedging solid. Same helix. Two completely opposite jobs, separated by the angle of a triangle. And that distinction, hold versus move, is really the fault line running under this whole story. The screws in your chair are on the holding side. Everything that follows is on the other one. Which for most of history meant water. The first screw we have any evidence for was a wooden cylinder as long as a room, wrapped in a helical blade, sitting at an angle in a river. Turn the handle, and water climbs the spiral and pours out of the top, higher than it went in. It's called the Archimedes screw, and Archimedes probably didn't invent it. He gets the name because a Greek historian, Diodorus Siculus, wrote about it roughly 2 centuries after Archimedes died. There's also a cuneiform inscription from the Assyrian king Sennacherib, 400 years earlier, that some scholars read as a description of casting water screws in bronze. That reading is contested. What isn't contested is that Archimedes left not one word about it himself. What matters here is the mechanism, not the credit. Because look at what this machine actually does. Rotation in, straight line movement of matter out. Same trait as the jack, just applied to a substance rather than a weight. Along the Nile, machines like this lifted water out of the river and onto sand continuously, with one person walking a treadle. Egypt fed the Mediterranean on the back of that, and nobody has improved on it since. Every combine harvester moving grain into its tank is running an Archimedes screw. So is the auger under a snowblower, the one drilling fence posts, the meat grinder, the machine extruding pasta. Sewage plants use open screws to lift wastewater precisely because a big open spiral doesn't clog on things you'd rather not think about. The plastic within arm's reach of you almost certainly went through one. In 1946, James Watson Hendry built the first screw injection molding machine, using a rotating screw to force molten polymer into a mold, with the screw's own friction helping to melt it. By the industry's own count, something like 95% of injection molding machines are screw machines today. 2,000 years, and the answer to, how do I move this stuff in a controlled way, is still a helix. But moving material was the easy half. If you lived around the Mediterranean 2,000 years ago, your economy ran on 2 liquids: wine and olive oil. Oil wasn't a luxury, it was fuel, food, soap, medicine, and light. Getting it out of the fruit efficiently was the difference between a farm that worked and one that didn't. The first answer was brute leverage. An enormous wooden beam hinged to a wall, fruit crushed beneath it, and ropes with a stone weight hauling the far end down. It worked. It also needed a crew, a lot of rope, and a building big enough to hold a tree trunk. Then somebody put a screw at the end of the beam, threaded it through a fixed frame, and anchored the bottom to a heavy stone. Now, nobody hauls anything. 1 or 2 workers walk around the screw, pushing on levers. The screw tries to lift the stone. The stone doesn't move. Therefore, the beam comes down, slowly and controllably, with a force no crew could produce by pulling. We're not guessing. There's a Roman sarcophagus relief at Aquileia showing exactly that. Men working a screw against a weight stone, carved by people who watched it happen. Then came the real leap. Somebody threw away the beam, the wall, the weight stone, and the building, and put the screw directly over the fruit, pressing on a stack of boards. A carbonized press of that type came out of Herculaneum, buried by the eruption that killed Pliny the Elder. That machine is smaller, cheaper, and one person can run it, which is what turns a technology from a rich man's installation into something an ordinary farm can own. And once you have a machine that produces controlled, enormous, repeatable pressure in a small space, it stops mattering what you put underneath it. Put a die and a silver blank under there, and you don't squeeze the metal, you reshape it. That's how coins stopped being hammered and started being struck. Put paper and inked type under there, and you have Gutenberg, who didn't invent a press so much as borrow the wine press standing in every Rhineland village and point it at a page. That machine printed at about 250 sheets an hour and barely changed for 3 centuries. Same machine. Olives, money, books. So by the Roman period, the screw is doing 2 jobs superbly. It moves material, and it generates force. But there's a third trick hiding in the helix, and it's the one that eventually matters most. Mesh a screw against the teeth of a gear wheel instead of a nut. Now the rotation bends through 90 degrees, and the reduction is enormous. 1 full turn of the screw advances the wheel by exactly 1 tooth. 30 teeth, and you have 30 to 1 out of a single pair. That's the worm drive. And it comes with the same friction bargain as the jack, turned up. Turn the screw, and the wheel turns. Try to turn the wheel, and often nothing happens at all, so a load hangs there without anyone holding the crank. You'll hear that stated as a law of worm gears. It isn't, and this is where most explanations get lazy, so let's do it properly. Self-locking depends on the relationship between the worm's lead angle and the friction between the surfaces. A worm with a 5-degree lead angle and a friction coefficient of about 0.13 gives a friction angle of roughly 7.4 degrees. More than 5, so it locks. Now shake it. Vibration can drop that coefficient to 0.08. The friction angle falls to about 4.6 degrees, and now it's less than 5. The gear can backdrive. The load starts to creep. Self-locking is a condition, not a promise, and you pay for it in heat. A worm drive in that range may be running at only about 40% efficiency. The oldest documented use is Hero of Alexandria's dioptra, a 1st century surveying instrument with worm drives on 2 axes. And here's the thing that matters about it. The dioptra had a scale. You didn't just move the sighting arm, you counted. Turn the screw a known number of times, and you know exactly how far you've moved, to a precision far below what your hand could manage or your eye could see. That's the third trick, and it's the big one. A screw of a known pitch doesn't just convert rotation into motion, it converts rotation into a number. And then almost nobody did anything with that for 1600 years. The man who finally did was a young Yorkshireman named William Gascoigne. Around 1638, he was working with a telescope when he found a spider had spun a thread across the tube and noticed that the strand sat perfectly sharp in the image. It was lying exactly in the focal plane where the picture of the sky forms, which meant anything else placed there would be sharp too. So he built it. 2 thin metal pointers in the focal plane and a screw of known pitch to drive them together or apart. Sight a star. Wind the pointers in until they just touch its edges, count the turns, and the gap between 2 objects in the sky becomes a number written down in a notebook. Not an estimate, not a comparison. A measurement, taken with a screw, of something nobody could reach. That is the same machine as the dioptra, and the same machine as Hero's thread cutter. A known pitch, a counted rotation, and a distance that falls out the far end, whether it's a thread being cut, an angle being set, or the width of the moon. Gascoigne was killed at Marston Moor on the 2nd of July, 1644, somewhere around 32 years old. His instruments were lost. The method survived only in letters, drifting to Richard Townley and eventually the Royal Society, and wasn't properly published until 1725, more than 80 years later. In the meantime, French and Dutch astronomers reinvented the whole thing from nothing, with no idea it had already been done, which is the first hint of what this pattern is actually worth. Lose the man, and you lose 80 years. The only reason that stopped happening is what comes next, which is where this stops being about pressing olives. Here's a problem that sounds trivial and isn't. Cutting a thread on the outside of a rod is fiddly, but doable by hand. You can see it, reach it, file it. A nut needs a thread on the inside of a hole where you can't see, can't reach, and can't file. And until you can make internal threads, the screw stays a curiosity, because a screw with nothing to screw into is just a spike. Hero solved it, and the way he did it is the hinge of this entire story. He started with a block of wood with a hole bored through it, and drove sharpened dowels in from the outside at an angle matching the pitch he wanted. Those protruding dowel tips form a thread, an internal thread made without ever cutting one. Then he cut an external screw the ordinary way and fixed a small metal cutter to an extension at its end. Run that screw through the dowel block, and the block acts as a nut. The screw advances at a fixed, known rate, dragging the cutter through the workpiece in a perfect helix. Raise the cutter slightly, run it again, deeper each pass, and you have bored a thread into the inside of a hole. Now stop, because what actually happened there is not about threads at all. That machine has taken the skill out of the operator and put it inside the mechanism. It takes a genuine craftsman to cut the first master screw. After that, somebody with a fraction of the training turns a handle and produces complex, accurate parts over and over, identically. And notice the shape of it. A handle, a master screw, a workpiece dragged past a fixed cutter. The accuracy that was in the master thread ends up in the new one. Remember that pattern. I'm going to point at it twice more. So, when does the screw finally become the thing in your chair? Very late. You have to jump to Germany in the last decades of the 15th century, to a region with the best mining, metalworking, and clockmaking in Europe. That's where metal screws start appearing as fasteners, and the first place you find them is in plate armor. Not everywhere in the armor. Rivets held most of it, because rivets were cheap and permanent. Screws show up in expensive tournament armor, in the specific places where a piece had to come off and go back on. Sometimes the screw was simply driven into a thickened area of plate, cutting its own path as it went. Quick note, because it will otherwise haunt the comments. Broadly, a bolt passes through an unthreaded hole and takes a nut on the far side, while a screw goes into the material and mates with a thread. Broadly. There are enough exceptions to collapse the distinction entirely, and I'm going to use the word screw for both. Fight about it below. And if there are screws, there must be screwdrivers, except there weren't. Screws were still rare enough that nobody made a dedicated tool. A driving blade got added to the handle end of something else. The multi-tool isn't modern. It's what you do when a fastener isn't common enough to earn its own drawer. Which brings us to a book I find genuinely startling. Somewhere between 1475 and 1490, in Germany, someone compiled what's now called the medieval house book, kept at Wolfegg Castle. Part manual for a lord, part sketchbook, and full of the new technology of the day. There are screws setting the elevation of cannon on 2 axes, which is the dioptra's logic pointed at an army. Fine adjustment, held in place, repeatable. As far as I can tell, nobody has found another illustration of a gun built that way, so treat it as an idea being drawn rather than standard practice. There are screws in the torture instruments, which is where the phrase about turning the screws comes from. The illustrator bothered to draw the slot in the screw head, which tells you the slot mattered to him. And then, on the back of a page about assaulting a tower, there's a screw-cutting lathe. It's drawn in 2 parts. The frame, with the master screw, and a workpiece that already has threads started on it. And separately, so you can see it properly, the cutting assembly that drops into the slot underneath and wedges in place. It has a removable cutting bit, the same principle as a tool bit in a lathe today. And it has a cross slide, advanced by its own internal screw, so the cutter can be fed deeper on each pass. That is Hero's machine, refined and reversed. Copying external threads instead of cutting internal ones, master screw dragging the work past a fixed tool, accuracy transferred from the old thread to the new one. 1,500 years later. Same pattern. Second time I've said it. The draftsman made one mistake, and I love him for it. The master screw is right-handed. The screw being cut from it, which ought to be an exact copy, is left-handed. Somebody drew the future beautifully and wound it the wrong way round. There's also an argument about whether the tool drawn alongside is the first illustrated screwdriver in existence. Some scholars say yes. It looks recessed to me, which would make it a nut driver for the end of that cross-slide screw. Either way, it's among the earliest pictures of a hand tool built for one job, turning a thread. A generation later, around 1505, another German manuscript, the Löffelholz Codex, and screws are on nearly every page. Clamping work to benches, which is the ancestor of every vice in every workshop. Inside compasses and calipers, adjusting them finely, which means somebody was already cutting threads delicate enough for instruments. And more thumb screws, because people are consistent. Then gunpowder finishes the job. The wheel lock mechanism borrowed heavily from clockmaking and was held to the stock with screws, not decoration, because a firearm delivers a violent shock every time it fires, and a screw biting into wood holds against that far better than a nail. Armor screws were made one at a time for wealthy clients. Gun screws were needed in quantity, forever, for a product in constant demand. That's what created dedicated screw-making trades in Germany and France. The screw became a commodity because of guns. Now the pattern does something strange, and this is the payoff. A screw can cut another screw, which means the accuracy that lives in one thread can be transferred into the next one. And if you're clever about averaging out the errors, each generation can come out better than the one before. It is, as far as I know, the only machine element with that property. Every precisely threaded object in the world is descended from an earlier screw, in an unbroken line running back to somebody filing the first one by hand. That inheritance is why Henry Maudslay's screw-cutting lathe around 1800 changed manufacturing. He didn't invent the idea. He inherited it, sharpened it, and industrialized it. And because his lead screws were better than anyone else's, the screws that came off them were better, and the machines built with those screws were better again. But that raises the obvious question, and it's the one the whole chain hangs on. If every screw is a copy of an earlier screw, and no copy is perfect, then errors should accumulate. Each generation should be slightly worse than the last, the way a photocopy of a photocopy degrades. So how does the line get better instead? Because a screw's errors are measurable, and anything measurable can be corrected. Cut a long screw from your master, and it won't be perfect. Over 5 feet of thread it might gain or lose a fraction here, drift back there. But you can find out exactly where. Run a nut down it against a fixed reference and watch where it arrives early and where it arrives late, and now you have a map of your own machine's lies. Then you correct for them. Maudslay's shop and the ones that followed used tricks like cutting a long screw, measuring its drift, and building a compensating bar into the lathe that deliberately pushed the tool the other way, feeding the error back in reverse so the next screw came out truer than the one that made it. That's the difference between copying and inheriting. A photocopier can't tell you where it went wrong. A screw can, because its mistakes show up as distance, and distance can be counted. By 1805, there was a bench micrometer in Maudslay's workshop, so authoritative the men called it the Lord Chancellor. When it ruled on a dimension, the argument was over. Joseph Whitworth trained in that shop and went further, building measuring machines that worked by touch instead of sight, a small pivoted piece that drops the instant contact breaks, because a fingertip beats an eyeball. In 1859, he demonstrated one that could detect an iron bar lengthening simply because somebody had touched it. Think about what that means alongside Gascoigne. He measured the sky with a screw, and the knowledge died with him at Marston Moor. 200 years later, the same trick is running in a Lambeth workshop, and it doesn't die with anybody, because it isn't in a man's head anymore. It's in the machine, and the machine makes more of them. Third time. Handle, master screw, workpiece, cutter. Every time this pattern shows up, the amount of skill a human being needs goes down, and the accuracy of what comes out goes up. And then, in 1877, in Menlo Park, New Jersey, a man used exactly that arrangement: a handle, a master screw, a cylinder advancing past a fixed point, and instead of a cutting bit, he put a needle on the end, with a diaphragm behind it. He turned the handle and spoke into it. The needle traced a groove into tin foil. Then he ran it backwards, and the machine said, "Mary had a little lamb," back to him, in his own voice. Thomas Edison said the phonograph was his favorite invention out of all of them. There's no evidence he was thinking about Hero of Alexandria, or a German draftsman, or Maudslay. More likely, it's what happens when people who understand screws hit a problem that needs something to advance at a perfectly even rate while a tool works on it. You reach for a helix because there still isn't a better answer. His cylinders eventually lost to flat discs. The principle didn't lose. The first recorded human voice exists because a screw turns a rotation into a distance you can count on. So look at what this shape actually did. It traded distance for force and lifted a city out of a swamp on the strength of men giving a handle half a turn. It moved the Nile onto sand, and it's moving grain and molten plastic right now. It pressed olives, then coins, then the first books in Europe. It bent rotation through 90 degrees and held a load in place with nothing but friction. It turned a turn into a number, so a man could measure something smaller than he could see. And then it did the thing nothing else does. It made a copy of itself and handed its accuracy forward and kept handing it forward until it could scratch a human voice into foil. The screw holding your chair together is real, and it's useful, and it's the least interesting thing this object has ever done. Have another look around the room and see if you can find one doing an actual job. Moving something, lifting something, adjusting something, holding tension. There's almost always at least one, and it's rarely the one you'd expect. Tell me what you find. Subscribe, because there's a second half to this. Once every workshop could cut threads, they all cut different ones, and nothing fitted anything. Sorting that out took 100 years, 2 world wars, and a fight between 2 engineers who each thought the other was wrong about the shape of a triangle. I'll see you then.